Fantastic. So there's a very exciting video by OKGo, flying in a plane, demonstrating exactly this principle. Um, but we're going to learn the math that goes with it. Let's see. This, yes, is example 4. I thought I would just warm up the class. Example 3 is more important, but it just, huh? No, we didn't. You should have example 1 and 2, which is a penguin being pulled like a sled horizontally, and then he's pulled at an angle. Okay. Uh, we we will go back to 3. I decided to warm up because that one's more interesting. The accelerating up and down, and the the possibility of actually being weightless. And then if we consider this carefully, it really helps with example 4. In other times when I am sort of, I feel like after those first 2 tests are so easy, I have to smack people and tell them, not physically, but I have to show people how complicated this can get and the complicated stuff that's going to be on this, and that's example 3. But I feel like you're appropriately cautious and still working hard, so we can do 3 first. It's the fun one. So yes, they are out of order if you're keeping track of chronology. Okay, so we're imagining that there's a scale underneath this person, and we don't have a cool enough elevator to try this at home, or try this ourselves, but you can try it at home. You can stand on the scale, and you might think that it measures your weight in gravity, but it doesn't. Okay, it tells you your weight. It figures it out by measuring the normal force. Okay, what the scale is. So there's a person looking down, sort of drawing. There's a spring under there, and what it does is it tells you how much force the spring has to exert up on you to stop you from smashing the spring anymore. Okay. We'll learn later in later chapter how springs work. It's actually a really simple system. That's how you can make a scale that's just a needle, and it doesn't really, you don't need a digital one or anything like that. I don't know how sophisticated digital ones even are. But if you doubt that it's measuring your normal force, put the scale next to like the bathroom counter, and then stand on the scale and push down on the counter. You didn't magically get lighter, but you'll see the scale go down and down and down because the scale is no longer supporting your full weight. It's supporting your weight minus whatever you're pressing on the scale on the countertop. Okay, lifting yourself a little bit. Okay. So, first we have to buy that the scale is measuring the normal force that it exerts up on you. Okay, and now we can do, this is a famous Albert Einstein experiment. Okay, if a person is in the scale, let's see, is on a scale in an elevator, and they say they accelerate down. Okay, so my acceleration, let's say it's minus 2 meters per second squared. We're going to accelerate down at 2 meters per second squared, not in free fall. That has to equal the sum of my forces. So it has to equal, we'll put vectors, the normal force vector, which would point up, plus the force of gravity vector. We might say the normal force is, oh, I don't really know what it is. Let's do plus F sub n. And then my force of gravity is always downward mg. And I have to divide by the mass of the person. Okay. For the sake of our example, let's say mass is Whitcomb's mass. It's a nice 100 kilograms. Close enough. Okay. Well, so then, actually let's multiply, let's do ma equals F sub n minus mg. Okay, so if a is minus 2, then we have minus 200, minus 200 what? If I multiply 100 kilograms times 2 meters per second squared, it's 200 newtons. If you knew that right away, then pat yourself on the back and stop writing down units in your equation. If you didn't know that, you better start putting these are all forces. If I'm going to add and subtract forces, they better all be forces. They better all be in newtons. It should be a helpful way to check, because you're remembering that kilos times meters per second squared gives you newtons. Okay, the normal force is what it will show on the scale, and I'm not sure how much that is if I'm accelerating down. But I do know that the Earth attracts me with my fabulous 1,000 newtons. Oh, and you can see right away that force must be 800 newtons pointed up to make up the difference. So this scale would actually say, it would read, if it was a metric scale, I weigh 80 kilos now, or I have a mass of 80 kilos. Such bad handwriting. Sure. That's exactly what happens. Will get rid of 10% of the weight. It's a coincidence that I'm approximately 100 kilos myself. Yeah, it will get rid of 10%, exactly. Okay, you could rearrange the algebra. You could take this. This is an awesome equation that will come in handy in example 3 and on the test. My net force is my mass times acceleration. Well, that's just the sum of the other forces. If I'm accelerating up or down, I still have the force of gravity near the surface of the Earth, and then the other force, if there's any support, that's the normal force. Okay, so you could just divide by g, and you would see, you could combine these terms on the other side and divide by g, and so your normal force, oh no, you wouldn't, you would factor out the same m. Okay, but yeah, because g is 10, whatever portion or fraction the acceleration is of 10, you're going to remove that much of the weight. If you accelerated up at 2, you would weigh 20% more, or 3 could be 30% more, 5 is 50% more. Okay? So you get extra heavy. Well, and curiously, you feel extra heavy. The pressure in your body increases if you increase. And Einstein was fascinated by this experiment. He had dangerous, clunky elevators back around the turn of the 20th century, way back when, 1900 I mean. So he said, well, okay, if I was in an elevator falling at 9.8 meters per second or 10, I would be weightless inside the elevator. How is that different from being weightless way, way out in space, far away from everywhere? What? And then he went around and asked everyone that, and the answer is there's no difference. There's no way to tell the difference. And so he said, well, wait a minute. Then how can we decide whether there's a force of gravity or what it's doing if all you have to do is fall straight down and then suddenly gravity disappears? Ooh, because it's called the theory of relativity. I suppose, and for now that'll do. If we're going to solve these problems, we have to assume that there is force of gravity, because it becomes a lot more complicated if there isn't. So, keep to that. There's always an mg force pointing down, and g is 10. Let's see. Do we feel like playing with that some more? No, we're okay. Okay. Let's do the hard one here. I'll break my video so I don't go over time.